12 o'clock, so it's around time for us to get started. I know your test was on Friday. I'm still marking them. They're not done yet. Hopefully they'll kind of only be another few days. I'm doing my best. I've got a test in my other course on Thursday, so I'm trying to get all of yours marked before Thursday. So that's kind of my goal, is to have them ready for you for Friday. So we'll see. What we did last Wednesday was we looked at a charging RC circuit. There's the highlights of how that works, and there's a problem. I'll post the answers here for this bit. We also started magnetic fields. We said that magnetic fields were made either by permanent magnets, like ones you stick on your fridge, or by moving charges. We talked about the force on a moving charge equals QV cross V. That was where we ended up on Wednesday. This is sort of interesting when you think about it, right? So we have magnetic fields just like we have electric fields. Magnetic force is the charge times the field. That's electric force is charge times electric field. Magnetic force is special and weird, right? Because it's a cross product, it means all of these things are perpendicular. If V is not perpendicular to B, you don't get a force. That's weird, right? The direction of the velocity impacts the force, and if there's a force or not. And the fact that it has to be moving at all, if it stays still, there's no force. That's weird too. So magnetic forces are just kind of weird, and I think that's sort of interesting. So anyway, we're going to keep going on that F equals QV cross V. The last thing we did on Wednesday before we had to quit was an example of finding the force. And I thought we would do a few of those today just to make sure we're okay with how to find them, using both methods. So this was the one that we did last on Wednesday. So as a refresher, for your right-hand rule, and the right hand applies to positive charges, you stick your thumb in the direction of velocity, so straight towards the ceiling. People who do this along with me are more likely to get it correct on the test. So if that matters to you, you might want to do it along with me. B is pointed towards that wall. You stick out your middle finger. You ask which way does that point? Straight into the screen. That's represented by an X, like we're looking at the back end of an arrow flying away from us. So that's what that X means. So with our notation, if you think about an arrow, if you look from this end, you see an X. If you look from this end, if you look from this end, it looks like a dot because the arrow is coming at you. Okay, let's do another one on this page. What about this middle one? What is this force going to be? Anybody want to say what they think it is? So it's sort of like a trick question. Not exactly, but a testing question. So you want to point your thumb in the direction of V. That's not so hard. You might have to twist your arm a little bit, but you can get your thumb to point towards that wall. Then you want to stick out your index finger, and you also want it to point towards that wall. I can't do that, okay? I can't make my hand do that. So here's a case where my V and my B are parallel. So that means whenever they're parallel, your right-hand rule, you just can't do that with your hand. It means the force equals 0. FB equals 0. We can also use our equation. I probably use the equation for myself more often than I would ever use a right-hand rule, because I can remember equations better than I can remember right-hand rules. So if we were using the equation, our force, we've got a positive charge, so we'd have a plus here. And then where the direction of V is towards the right, that's the X direction, or I hat, crossed with the direction of B, also to the right, or I cross I is equal to 0. Okay, so you can always do the math or the right-hand rule. They will get you the same answer. Okay, I'm going to leave this one for a homework problem. And then we'll do a few more examples. If at some point when I'm doing the examples, you're kind of bored and you say this is enough, just let me know and we'll stop. So for this one, let's look at the third one on this page. And it may or may not catch your eye that I've picked a negative charge here. So your thumb goes with your V, so it's sort of up to the corner of the room. Your index finger goes with your B, that points towards that wall of the room. You extend your middle finger and you ask, what does that do? It should point into the screen. Here's where you have to remember that your right hand rule is for a positive charge. If your charge is negative, you have to rotate your answer by 180 degrees or just flip directions. So a positive charge doing this would have a force into the page. This is a negative, so the force must be out of the page. So there's the magnetic force. If you like the equation, then your FV is Q cross V. Your Q is negative. Your V is up and to the right, so that's I plus J, got both components. Cross with your magnetic force, that's to the right, so that's an I direction. So this would be negative outside of I cross I plus I cross J. I cross I, that's 0. I cross J. I am assuming that you've all seen cross products, either Physics 1051 or a linear algebra course or maybe somewhere else. The way I remember all these IJKs, my first year physics prof showed me, and I've used it ever since. You put IJ and K in a triangle, they point from one to the other. As you go the right way around the circle, you get positive results. If you go the wrong way, you get a negative. So I cross J, we're going the right way, we get plus K for our answer. So I cross J is plus K. You might have another way you remember those. If you have another way, that's absolutely fine. So our answer is negative 0 plus K or negative K. Positive Z is out of the page. Negative Z is into the page. That's all right. Oh, look, I did it wrong. Here is J cross I, and I wrote I cross J. I'm so sorry. I don't like when I make mistakes. J cross I. J cross I goes the wrong way around the circle, gets us negative K. Negative times negative gives us positive. Okay, any questions? I'll leave the other two for homework. Let's do another one where the magnetic field points out of the page. So let's do the middle one. We've got a positive charge. Our velocity points this way. So our velocity is going this way. Magnetic field is those dots, so they're pointed out of the page towards you. You put out your middle finger, it points towards the ceiling, so the direction of the force is up. So there's our FB. If you did your equation, you would have your FB is the sign of the charge, that's plus, direction of V, that's minus I hat, crossed with the direction of B out of the page is plus K hat, gives us minus I cross K. I cross K gives us negative J plus J or up. Okay, so math or right hand rule, doesn't matter which one you go with. Questions? Okay, next, why don't we look at this one? So we're off at an angle here. The charge is negative. Velocity is up this way. Magnetic field is out of the page. So let's see if we can get the direction of the force. So your thumb has to go with your velocity, sort of up this way. Your finger has to point, it's starting to get painful. So your V goes this way. Your finger goes this way, so your magnetic force is going kind of up and to the right this way. So my V is going up this way, my finger is coming out towards you. I look at what my finger is doing, and it's pointing this way. Why don't I try and do it on the page? So my V goes this way, F goes this way, or my magnetic field comes up like this, and then my index finger comes up this way. So what my finger does is comes up this way. This would be the force on a positive charge. Our force has to come this way because it's negative. So there's your FB. When you have F as QV cross B, it means that your magnetic force is perpendicular to both your velocity and your magnetic field. That's the nature of a cross product. So F is perpendicular to both of these guys. So if you did this diagram, You probably put a perpendicular mark in there just to show the angle. If you wanted to do the math, FB equals negative for my charge. V is negative I plus J, so left and up. Crossed with my B, which is out of the page, that's K. So that's negative outside of minus I cross K plus J cross K equals I cross K is negative J. So that negative outside of negative, negative J plus J cross K is plus I equals negative outside of J plus I, negative I minus J. Okay, so left and down. So either way you like it, absolutely fine. Okay, for this one, let's look at the first one. So V is up, V is into the page, force is pointing out this way. So your thumb goes up, V is into the page, and our force comes this way. So V, B, force. There's our magnetic force. I think I won't bother with writing out the I's and J's and K's this time. Very last one. Let's look at this one. We've got a negative charge, so we put our V going this way. Your V goes with your velocity. Your B is into the page. Extend your middle finger. You see it points up, but we've got a negative charge in our picture, so we've got to rotate, and the force actually points down. There's our magnetic force. So your V goes with your velocity, B is into the page, you extend your middle finger. This would be the force on a positive charge. Negative charges are always rotated by 90 degrees. Okay, there was a whole whack of practice ones. Any questions? So then there's a bunch more. There's 2 extra ones on every slide for you to get for homework. It probably feels like a little bit of busy work, but you know, you can make a mistake with these. You know, practice is the only way to get really comfortable with it. Or doing the math too, like both is right. Okay, so let's go from this to an example with some numbers in it. So a beam of protons, right off the bat when you read beam of protons, it means you know what the charges are. Q equals plus the fundamental charge plus 1.6 times 10 to the minus 19 coulombs. Moves through a uniform magnetic field with a magnitude of 2 teslas. So the magnitude of the magnetic field is 2 teslas. We see in our diagram that it's along the positive z-axis. So if we wanted to write it as a vector, 2 teslas in the k direction. The protons have a velocity with a magnitude of 3 times 10 to the 5 meters per second in the xz plane at an angle of 30 degrees. So we're in a plane with the magnetic field, and it points out kind of partly in x and partly in z. So our velocity is 3 times 10 to the 5 meters per second, and I'll just say at 30 degrees, going along with the picture. Right off the top, if you wanted to, you could go ahead and find the components of the velocity. You know, there's a z component and an x component. You could use your sine and cosine to find those components. So if you wanted to do the vector components, you certainly could. Find the magnitude and direction of the force on the proton. We have 2 choices. We can find the magnitude using q, v, b sine theta, and then use our right-hand rule for the direction. Or we could do it using the equation. I think for this example, why don't we do it both ways? Then you'll see how to do both ways, and you might decide if you're getting a preference of which way you prefer to do it. I wouldn't say either way is easier or harder or simpler. They're just different. So let's go with the right-hand rule on magnitude first. So the magnitude of my magnetic force equals the magnitude of my charge times the magnitude of my velocity vector times the magnitude of my magnetic field times the sine of the angle. Let's just be really careful here with our angle. An angle always means an angle between two things. The two things it's the angle between are the velocity and the magnetic field vectors. In this case, the angle is pretty straightforward. It shows you in the picture that the angle is 30 degrees. But a twist could be on this problem, that this angle would be given as 60 degrees. Then it would be tempting just to plug in 60 because that's the angle that's given. So you always got to stop critically and ask, where is V, where is B? What's the angle between those two things? So that angle matters. So let's put our numbers in. 1.6 times 10 to the minus 19 coulombs. Magnitude of the velocity vector, 3 times 10 to the 5 meters per second. Magnitude of the field, 2 teslas times sine 30 degrees. So the magnitude of our magnetic force is 4.8 times 10 to the minus 14 newtons. Okay, then we have to get our right-hand rule. So your arm's going to get a bit twisty here. So V, if we take Z as coming out of the page towards you, so V is partly this way in X and partly towards you in Z, so more or less this way. Magnetic field is coming towards you, so sort of like this. And then your extended middle finger points towards the ground, so your force points down towards the ground or the negative Y direction. So we've got a minus J hat, and in brackets we would say that we found a direction using the right-hand rule. Okay, if you don't care for that method, you can always do the math method where we think about the vectors. Both should get you the same answer. So let's say if we use the vector product. So FV equals QV cross B. I tried to be careful here. When we were doing the magnitude of the force, we used the magnitude of the charge. If we're using the vector equation, we put in whatever the charge is, positive or negative. So up here it's a magnitude, here's whatever it is. So what are we going to put in here? Charge on the proton is just E. For our velocity vector, velocity is 3 times 10 to the 5 meters per second at 30 degrees. So it's got an X and Z component. The X component is over here. The Z component is over here, or here and here. So there's our Vx, there's our Vz. So our velocity is the X component in the X direction, plus the Z component in the Z direction. For our X component, Vx equals V times sine 30. And our Z component, Vz equals V times cosine 30. We're still good here? You could calculate those numbers straight away if you wanted to. I don't want to just yet, so I'm not going to. But if you were more of a numbers person, you might do that right away. Okay, so there's our V, is Vx in the I direction, plus Vz in the K direction. That's going to be crossed with the magnetic field. For the moment, I'm just going to call that B in the K direction. I'm trying to go symbols first. So B is 2 teslas in the K direction. The magnitude of B is 2 teslas. So if I apply my distributive property, I get E times Vxi crossed with B times K, plus Vk in the K direction crossed with B in the K direction. Okay, so I just multiplied my terms out. I've got E outside, and I or I use a distributive property to get my B inside. So that's the same as E. Vx and B are just scalar quantities. They can come to the front. And I'm left with I cross K in the back. Plus Vk times B, K cross K. Good to hear. So let's look at what we have in our equation now. K cross K, that's 0. So you can't do something cross itself. Two parallel things with a cross product is equal to 0. I cross K, that's minus J. So for our next line, we can write down E times Vx times B in the negative J direction. Negative E Vx was V times sine 30 degrees times B in the J direction minus E times B sine 30 J hat. The reason I wrote it out in symbols the whole way was hopefully so you could see that this is the same as this. So exactly the same answer, right? So that's good. Two different methods, same answer. I won't bother to write the numbers in again. We get minus 4.8 times 10 to the minus 14 newtons of J hat. So if you have a test, you're trying to calculate the magnetic force, you can go either way, whichever way you find easier for yourself. Okay, any questions? All right, so I've got two similar problems that I'll post as homework questions. And then we'll get to thinking about, okay, if it feels this force in this magnetic field, what is the motion going to look like? That's kind of an important question. Any questions? So let's say we have a proton and it's shot into a magnetic field that points into the page. What is the motion going to look like? Is it going to swerve up? Is it going to go straight? Or is it going to swerve down? I'll give you a second to think about it, and we'll see what you can decide. Okay, any decisions? Okay, maybe we'll do a show of hands. Who likes 1? 2? 3? Okay, a little bit of variety there in the answer. So let's apply the right-hand rule. So the velocity is going this way. So velocity, your thumb needs to be pointing towards that wall. Your magnetic field is into the page. So this finger has got to go into the page, and you've got to turn your hand around. So that can be a tricky bit, right? Trying to twist and turn your arm so it points in the right direction. So your V is this way, your field is into the page, the force points up. So this thing is moving to the right, it feels a force that points up, so that means it's going to swerve up. And then it gets over to here, it's moving this way, the force is still this way, it's over here, moving this way, force is this way. Okay, so path 1 is absolutely the correct answer. Okay, so what would an electron do?
The opposite.
Opposite, right? Proton is positive if that swerves up. Electron is negative. The force is going to flip, so the behavior would flip. I said that was going to be a homework problem, so you're 1 up on the game now with your homework. So for this one, the magnetic force would point down, and that downward force would cause it to swerve down. So opposite proton. Some problems, like you might see on a test, I could give you a question, and I would take you through what's the force and behavior for a proton. And then for part B, I might ask, what would change if this was an electron? And you wouldn't have to go through all the math again. You would just say, oh, they have equal and opposite charge, so the force would be equal and opposite. Like, it's okay to use those kind of symmetry arguments. Those are good to use. Okay, next. That's going to kind of expand a little bit about that proton motion. So we're going to ask, what's happening if the force and the velocity and the magnetic field are all perpendicular? So we're going to start, and we're going to put our velocity perpendicular to the magnetic field. So if we do FB is QV cross B, so QVB sine theta, the theta is going to be 90 degrees because it's perpendicular. So let's ask, what's the force on this positive charge that's initially moving upwards in this magnetic field? So V is up, B is into the page, the force points this way. So let's draw that magnetic force. There's our FB. This force is to the left while it's drifting up. So the motion is, it's going to continue to go up, and it's going to get pulled to the left. Okay? It's moving up, so it keeps going up. It's pulled left, so it moves left. So up and left is going to put us over here at some point. And it's moving up and left, so the velocity looks like this. So V is this way, B is into the page, our force is this way. So always perpendicular. So V is here, B is into the page, F is down and in. There's our FB. This is going to continue to drift to the left and move down a little and be pulled down, so slowing down this way. So it's going to end up over here, moving this way. So there's our velocity now. V cross B, now the force is straight down. So hopefully what's jumping out at you is that your force is perpendicular to the velocity. This maybe rings a bell from physics 1020 or 1050. When the force is perpendicular to the velocity, that's when you get circular motion. So it'll go around in a circle where the force provides an acceleration that changes the direction of the velocity. So what we're seeing is FB perpendicular to V, circular motion. So our equation, FB equals QV cross B, tells us that our magnetic force is perpendicular to the velocity, and our magnetic force is perpendicular to the magnetic field. This circular motion, when we're talking about motion in a magnetic field, we call it cyclotron motion. So that's the special name for circular motion of a charged particle in a magnetic field. So this is a picture I got straight from your textbook. I think it's kind of a nice picture, and they do a nice explanation in your book. So what's happening here is we have an electron gun at one end, so it makes a beam of electrons. We've got two big metal coils here. There's current flowing through those, so it makes this constant magnetic field. So the electrons are moving in a magnetic field. The electrons are coming in this way. The magnetic field is this way. Those two things are perpendicular, so it makes a force that's perpendicular. It makes the electrons go in a circle. What's neat about this is that this little container here is filled with gas. So the electrons are in the gas. They collide with the gas particles. That makes it give off energy, and it gives off light energy. So these circles here is showing the path of the electrons because it's colliding with all the gas molecules in this path. So this is kind of nifty, right? You can very easily measure the radius of that path, and that can help you learn about the charge and the masses of those particles that you can't even see, right? It sort of proves their existence, so that's kind of cool. So let's apply some physics 1050 analysis to this process. If it's going around in a circle, we can start with Newton's second law, sum of the forces equals mass times acceleration. Typically when we do all these problems, just like in our electric field stuff, electrons and protons are not very heavy. We pretty much always neglect gravity. So our force on the charged particle is our magnetic force. That's got a magnitude of Q times V times B times sine theta. So it's just the magnetic force. Whenever something goes in a circle, we say that our acceleration is V squared over R. So that's our circular motion bit. So our sine theta is going to be equal to 1 because theta is equal to 90 degrees. We've got V squared on this side, a V on this side, so we can divide through by V. And then we could rearrange to solve for R. That would be M times V divided by Q times B. Radius of path of charged particle moving in a magnetic field. I'll use a little bit of shorthand there. So if you measured the radius of the path, you could find the charge to mass ratio, which tells us a lot about atomic behavior. I'll give you a theory question just to ask yourself about. Does this magnetic force, F equals Q cross B, QV cross B, does it do any work? So maybe try and put that in context, see if you can figure that bit out. Okay, any questions here? Okay, let's try and do a circular motion example. So an electron at point A, an electron right here, has a speed of 1.41 times 10 to the 6 meters per second. Find the magnitude and direction of the magnetic field that will make the electron follow a half of a circle path going from A to B, and how long does it take to get from A to B? So let's see if we can figure out the direction of the magnetic field first, and then we'll try and figure out the size of the magnetic field. So let's look at what's happening. At the very beginning, over at point A, the electron is going upwards, so that's our velocity. The direction of the force is towards the center of the circle, so it starts to move to the left, so the force must be to the left. So there's the initial force. So our thumb has to be our VO. Our thumb has to go that way. Our extended middle finger has to be our force. So now I've got to rearrange my hand a bit. So my thumb is up this way. I'm doing my right hand rule like this. So my middle finger has to go out this way. Okay, so it's starting to get a little painful. I'll just move my paper a bit. So my V goes this way, my F goes this way. I ask what my index finger is doing. My index finger is B. It's pointing towards the ceiling. So your first thought might be that B has to point out of the page. Then you have to remember that your right hand rule applies to a positive charge. My charge is negative, so B must be into the page. Okay, so to get this force, you have to have a B into the page. If you prefer to do that using the equations, that's no problem. You'd say F is QV cross B. You know that your force is in the plus I direction, V is in the plus J direction. Your charge is negative, so you'd have to ask what B direction would give that answer. So if you wanted to go for the equation, that would be absolutely fine. Okay, for our magnitude, so that's the direction of B. We know that if we think about the forces on this electron, the sum of the force is mass times acceleration. So we can show our steps like we did on the last slide, and we would find that Q times B equals M times V over R. Okay, so all those steps on the last slide, the force is the magnetic force, QVV sine theta, but theta is 90 degrees, so sine theta is equal to 1. MV squared on this side, one of your V's cancel, and we get left with this result. So it would be okay to follow all those workings. We're trying to solve for our B. So the magnitude of the field is the mass times the velocity divided by the magnitude of the charge times the radius of the path. So M means the mass of an electron. 9.11 times 10 to the minus 31 kilograms. The speed, 1.41 times 10 to the 6 meters per second. The size of the charge is 1.6 times 10 to the minus 19 coulombs. The radius of the path, we get that from the picture. The radius is going to be half the diameter, so 5 centimeters. So the size of the magnetic field is going to be 1.61 times 10 to the minus 4 Teslas. Okay, so our magnetic field direction is into the page, and the size is 1.61 times 10 to the minus 4. When you do this for homework, repeating for a proton, because the proton is positive, we're going to get the opposite direction for the magnetic field. Because the proton has a different mass from the electron, we'll get a different value for the magnetic field. Okay, so same concepts, but we're going to get different answers for a proton. So there's part A. Part B is how long does it take? Well, if we remember our definition, our speed, which is going to be constant, is distance over time. The distance it travels is 1/2 of the circumference of a circle. So from A to B, it goes to 1/2 of a circle. So 1/2 of 2 pi r divided by t. And those twos cancel. T is going to be pi times r divided by v. Gives us 1.11 times 10 to the minus 7 seconds. That's a very short time, but then these particles too tend to be zipping pretty fast, right? So it doesn't take long for them to travel a small distance. Okay, questions? So now the next thing we'll do is let's think about a little bit different part of our V. What if our V has 2 components? So what if V has a part of the velocity perpendicular to the magnetic field and a part of the velocity parallel to the magnetic field? Okay, so that's kind of an interesting thing. And we could certainly have that happen. So this is a neat video. The team at St. Mary's put together a lot of really nice videos. So I'm going to play one of those.
Of an electric charge in a uniform magnetic field. Because the magnetic force depends upon the cross product of the charge velocity and the magnetic field, the motion is usually 3-dimensional. We will start with the special case where the initial motion is perpendicular to the magnetic field. In this case, the resulting motion will only be 2-dimensional.
So this is the first bit we
and hence
did.
the acceleration is always perpendicular to the velocity of the charge, the resulting motion of the charge will be circular. The force on a negative charge will be reversed compared to a positive charge with the same velocity. As a result, positive and negative charges will traverse their circles in opposite directions. Speed also affects the radius of circular motion. However, the time it takes is not affected by the speed. The frequency of orbits only depends upon the charge, the magnetic field strength, and the charge's mass. Returning to the more general 3D case, the net motion of the charges will be determined by the parallel and perpendicular components of the charge velocity relative to the magnetic field. The component of velocity parallel to the magnetic field determines the part of the motion along the magnetic field lines. This part of the motion is at a constant velocity. The component of velocity perpendicular to the magnetic field lines determines the circular motion around the magnetic field lines. The net result of these two motions is a helical motion, where the charges spiral around the magnetic field lines.
Okay, there's that video. I also have a very simple physical demonstration. So I just got a ball on a string. So if I have a magnetic field that points up from the floor, if my ball is initially going up, it'll just keep going up, right? Because there'd be no force due to that magnetic field. If my ball goes sideways, it's going to turn in a circle. If I put those two things together, I'll get circular motion from the perpendicular velocity and upward motion from the parallel velocity. So it just turns in a helix, right? So you get a helical motion. I think that's kind of nifty. So that's what happens when you get both components of velocity present at the same time. Back to the dot can. So the perpendicular part, that gives us the cyclotron motion, or the circular motion. And the parallel part, we say that just results in a drift. So it keeps moving with that same component of velocity with no change. And together, the path is a helix. Okay, questions? No, okay. So let's just go back to something they brought up in that video about the time and the frequency. So this is a picture of a cyclotron. I think this one is CERN. I can't remember where I took the picture from. I think it's CERN. So they have these particle accelerators, and this is what they do. They shoot charged particles in there. They go around in these circular paths as they go along the loop of the cyclotron. So that's what they do, and they do these all the time. They measure the radius, and they measure the time for one cycle, and then they learn lots of physics about the particles they shoot through it. So that's what they do. If we apply our straightforward analysis, if we remember that V is d over the time it takes, if we're thinking about one complete circle, then the distance would be 2 times pi times the radius of the path. The time would be the period for one cycle, so one turn around the circle. 2 pi over t, 2 pi over the period, that's angular frequency. So that means that omega, our angular frequency, is the speed divided by the radius of the path. If we remember that the radius of the path was m times v over q times b, so that's what we got from our straightforward analysis. Sum of the force is mass times acceleration. The force was the magnetic force, qvb, and it led us to this expression for the radius of the path. We find that that angular frequency is the charge times the field divided by the mass. So the angular frequency only depends on the charge and the mass and the magnetic field. It doesn't depend on how fast those things are going, so that's kind of a neat result. So the magnitude would be the magnitude of the charge times b over m, and then f would be omega over 2 pi, and that's what we call a cyclotron frequency. So studying these things helps us learn about the charge and the masses of all these particles. So it was a way that they studied all of those things. And then that brings us to kind of my favorite application of this helical motion. And that would be the Northern Lights. So how many people have seen the Northern Lights? I did just like a tiny bit. Like I was in a little southern community in Newfoundland, and it was real dark, so I got to see them a little tiny bit. It was not that impressive. My mom and dad lived up north for a while, and they say it is that impressive, so it's kind of on my list of things to see. So what happens is during a solar flare, a whole bunch of charged particles get blown off the sun, right? So lots and lots of charged particles are blown off the sun. They drift towards the Earth, where they come into contact with the Earth's magnetic fields. So these are moving charged particles around magnetic field lines. We get partial drift, partial circular motion. So they're drifting along the magnetic field lines going in a circle. It follows those field lines right down into the atmosphere. As it comes into the atmosphere, the charged particles are colliding with the atmospheric molecules, and it gives off energy in the form of light, so that's why it glows. Near the poles, that's where the magnetic field lines are the densest. It's where the field is the strongest. That's why you get these pronounced northern lights at the North and South Pole. I have heard reports, you know, I've seen people say on the internet, so who knows if it's true or not, that some people can hear the northern lights. I'm not sure that I buy it. Like, the northern lights happen pretty far up in the atmosphere. I'm not sure the sound could travel that far. I would like to try and verify it for myself, though. So I always ask people if they've ever heard the northern lights. I'm not sure I'd believe it if somebody told me they had, actually. Any questions? No? Okay. So the next thing I wanted to do was talk about magnetic force still on a charge, but start to talk about currents. But I sort of feel like we've done a lot for today. Are people okay if we quit 5 minutes early? I feel like this was a pretty dense class. Okay, so let's quit here, and then we can start nice and neat on Wednesday with currents. Yep.
I lost in the middle for a bit. In this example,
Yep.
I did this the cross product. I tried it this way. Where exactly am I inputting this side? I think I get something like this. In the end, you found the magnetic field by putting values for these.
Yeah.
Yeah. So where do I bring in the? I think it is for electrons. So
Yeah.
the negative sign cancels out.
Yeah.
Yeah, but okay, so does it, I mean, let's say this was k hat instead. Okay, let's say it was in some other direction. How much of a difference would it make?
Yeah, if it's a different direction, it would change
Okay.
the direction of the force, right?
Yeah.
Yeah, they all depend on each other.
Okay.
Yeah,
Okay, yeah.
yeah.
Okay, thank you.
You're welcome.
I emailed you about missing a problem session.
Yes.
And you told me I hadn't contacted them within the 48
Or I just
hours.
asked if you had contacted within
Yeah,
48
I
hours.
haven't. I didn't.
Okay,
I know there's probably nothing I can do.
let me think about it, because oh jeepers,